Okay, everybody. Well, thank you. Welcome back. I had the highly coveted role of giving the closing talk to try and summarize what we heard. Of course, it's all plenary sessions with no parallels, so many of you have already sat through this. So I'm going to try and pull out some high-level takeaways that I got out of the meeting. So just to back up a little bit before I get going, though, why are we trying to have this conference? So we tried to make the case over the last several years that due to advances in hardware and experimental techniques, we can extend spectroscopic reach far beyond what we have done up till now with something like DESI. And this opens the possibility of galaxy surveys that can start to surpass the CMB in terms of the amount of primordial physics loosely defined that they have access to. And this opens an opportunity for doing some science. And then the question is, can we explore that opportunity and see particularly what it means? Spectroscopic surveys are inherently incredibly powerful. The same instrument can do many different kinds of things, and that's great, but it's also a bit of a drawback in a way. We can prioritize different kinds of targets. We can prioritize different kinds of redshift ranges. We can prioritize different kinds of densities. There's a lot of potential to optimize the science return. So it's a little bit different from some other kinds of surveys. We could decide to go broad. We could decide to really concentrate and drill down in one area. And so in order to make some of these decisions in an informed way, we wanted to kind of gather theoretical input over, what are the science cases? What are we trying to do? Where is the best payoff as we start to define S5? So we got some nice tailwinds from the SNOMAS and P5 process. They said there's lots of great things that something like DESI 2, and stage 5 could do. And so we need to build on this, and we need to try and argue that this is something that we should actually be turning into an actual project. So it was already alluded to on the first day that there's multiple surveys hiding within Spec S5. There was a discussion of Milky Ways and dwarfs, a low Z, high number density survey. What I want to focus on, because it was most of the topics for this meeting, is this sort of high Z precision cosmology regime. I'll come back and talk briefly about the others a little bit later on, but for now, let me focus on that. We heard earlier on that EFT is sort of the unique large-scale solution in this area. One of the nice things about this particular science case is, in principle, it's easy to forecast and easy to optimize with the usual physicist definition of the word easy that all of my students are familiar with. And so there is a chance here where we really can go through and talk about, this is how I'm going to optimize the survey because this is the particular science goal I'm going after in a way that's harder in some other cases. Okay, so this has also been mentioned in the past. There's a lot of galaxies out there. We get to choose among them, right? We get to put fibers on these objects and take spectra, and we get to choose which things we want to do. This is a figure that's taken from a paper by Haruki Abina. The kind of pinkish blob there is the lensing kernel from the CMB. So you can see we have access to the matter field over this whole redshift range. The yellowish peaks are filters that we would use for target selection, medium band filters, in which the Lyman alpha line would fall into one of those filters, and we'd select objects at those given redshifts. Or we could have Lyman break galaxies that would give us redshift distributions like are shown in the blue, green, and red, and Christoph talked about that earlier. And of course, with the Lyman break galaxies, we can also do the Lyman alpha forest, which we heard about earlier today, right? So there's lots of different things we can go after here. We can choose the integration time per source, the number density, the redshift reach, the bias, whether we want high bias for looking at things like scale-dependent bias, or low bias to try and eliminate scale-dependent bias. So there's lots of ways of optimizing the desired science. The problem is that we are resource constrained, and so I can do lots of trades, but we can't do everything. And so we have to come to some decision about which of these things that we'd like to do, we should do. Okay, before I get going, let me just try and put a little bit of context about the way we've been thinking about this to some extent. As we push to higher redshift, a lot of things happen that are very good for us. In particular, the fundamental mode of the survey is moving to lower K, the nonlinear scale is moving to higher K, and we're getting a longer lever arm in time. So the dynamic range over which we have a standard spectrum, not just a BAO peak or something, but a full spectrum's worth of information, is actually quite large. And so one way of thinking about what is the science reach of something like stage 5 is that we're sensitive to anything that deviates from boring spectra. And I didn't say power spectrum. This could be a 2-point function, a 3-point function, a 4-point function. I'm agnostic. But anything that deviates from what we expect could in principle be interesting. And remember that we're talking here about things that deviate at the less than 1% level, right? So this is a high precision measurement with a wide dynamic range. This could be primordial, it could be induced by bias, it could be due to evolution, it forces, what have you. Anything that causes a deviation in the spectrum. What would be really great, I have no idea how we would do this, but what would be really great is could we turn this kind of idea into some kind of thing like the STU of precision electroweak or something like that, right? Is there something where I could take a bunch of these different science goals and say, oh, they can all be summarized in this nice basis? I don't know, but that's something we're thinking about. Okay, so the P5 panel referred to a lot of this science as the hidden universe. And I want to highlight something that has changed in the last maybe 5 years or so, is that for a huge number of years, galaxy redshift survey was more or less synonymous with dark energy, sometimes with dark energy and growth of structure. And so, when you went to DOE, that's what you were doing if you were doing a redshift survey and they didn't really care about anything else. I think there's a growing realization that just barely scratches the potential of what we could be doing with galaxy redshift surveys. And I believe now the funding agencies are even on board with that. It's much like, CMBS4 is clearly much more than just R. There's a lot of science you can do, and we need to really flesh that out. So during this conference, we've heard about a huge number of other science cases. I've just listed a few of them here: inflation, non-Gaussianity, parity violation, these somewhat ill-defined but kind of exciting cosmological collider, primordial features, axions, et cetera, et cetera. So our task essentially is to find compelling science targets that help us to design S5 so that we can convince the agencies that they should really fund it, right? So that's what we're trying to do. That's where we're trying to go. What we've done up until now is something slightly different. So we were designing a straw person. We've been fairly theory agnostic as to what that would be. The argument we made was that, wow, a lot of these new ideas sound quite interesting. I'm not entirely sure I want to bet my house on any of them. So if I want to maximize the signal to noise, but I don't really know where the signal is going to peak, one thing I can do is I can just lower the noise everywhere, and that will maximize discovery potential. And that's okay for setting up like a straw person design and for saying what sorts of facilities would I need to do that. Is this pie in the sky? I need something that's larger than the size of the solar system and the entire US budget for 1,000 years, or is this something we can actually build, right? So that's enough for getting us that far. But the next steps, I need to say what science will come from Spec S5 and how I will set priorities in a flow down study, with the idea being that if it's not required by something in the level 1 requirements, it's probably going to get cut, right? So now we have to go beyond this. This was great for getting us this far, but we need to go beyond this. And unfortunately, we'd like to make these decisions in the next year-ish timescale. And that's just based on experience with what we've done in the past, that we need to have these kinds of things roughly a decade before we actually want to be on Sky, and we'd like to be on Sky in the mid-2030s, right? All right. So here I've tried to break out the science cases that we heard about into this meeting. So back when we were writing the SNOMAS reports or the Astro 2020 reports, or what went, flowed into P5, we had things like dark energy, growth of structure. We'd identified stuff like neutrino mass and light relics, primordial non-Gaussianity, and so on. And then I've listed on the right-hand side a whole bunch of further topics that didn't really make it into, the SNOMAS white paper. Well, they're in some of the SNOMAS white papers, not the ones specifically about Spec S5, that have come up in this meeting that are definitely worth exploring and may actually be even more interesting in some ways than the stuff that's on the left. And to some extent, what we have to do in the next year or so is try and figure out what from this list of things is going to make it into the science goals of Spec S5 that then lead to the flow down to the survey design and the instrument design and the survey design. Okay. So let me just run through a few things that have come up throughout the meeting. We heard a whole bunch about cosmological tensions. It's interesting to notice that these things have cropped up as I've pushed the error bars below 1%. Right? We would not have a Hubble tension if the Shoes team and Planck had both measured the Hubble constant with a 30% error, right? It's only when we're starting to talk about these sort of percent level error bars that we see these tensions. It is not too surprising that in a model like lambda CDM, which has to be phenomenological, that as we start really pushing on it, we're going to start to get these tensions. So we can't ignore these sort of tensions, There's a rich experimental program that's investigating them. In addition to possibly being discovery potential, as we were told to call this, they do also have implications for other things we'd like to know. For example, some of these tensions impact on what we think the neutrino mass is and stuff like that, right? So we need to kind of sort of get this under control. The reason I'm going to skip over this and not really come back to it very much is that I think we have a fairly good idea how S5 would impact these sorts of topics, right? This is in some sense the bread and butter of what cosmologists have been doing for a long, long time. So I don't want to suggest that these aren't interesting, but I don't think we need to spend a lot of time talking about them today because they're the things we would normally do. Okay. Other things we talked about during this conference, one of them was neutrino physics. Neutrino effects are one of those things which we already have to include to do the calculations at the precision of current experiments. So this is the sort of the guaranteed science. Two signatures that we use all the time are the free streaming of the neutrinos and the mass. We've detected free streaming at redshift 1000, but not really yet today. The second is a goal, right? We'd like to detect neutrino mass if we at all could. And then what we heard is that non-standard neutrino physics can affect both the free streaming and trivially the mass, neutrino self-interactions, decays, and so on. And so these sorts of effects are the kinds of things that we could definitely go after with stage 5. They do get tangled up in existing tensions, right? Neutrino mass being the most obvious example. And so that ties these two kind of previous slides together. I've given this quote from the P5 report specifically about inflation. This was one of the things that we tried to highlight and one of the things that the P5 report latched onto, that you can think of Spec S5 as sort of an inflation probe. We sold this as kind of, in the past, we did the current generation of accelerating universe. And with Spec S5, we'll do the early stage of acceleration in the universe, right? So both epochs of accelerated expansion. They took a much more, open view and said, it can probe inflationary physics via the statistical properties of the primordial fluctuations, which is so suitably vague that I'm sure we could slide, almost a Mack truck through that hole. One of the things I think that we've heard about during the last 3 days is that there's numerous ways inflation could be different from the simplest models, right? There's a lot of space out there that's worth exploring. In addition to just measuring the tensor to scalar ratio, we've got the running of the spectral index, various higher order functions, primordial features, isocurvature modes, the cosmological collider, all of these various things. And we heard a whole bunch of talks about all of the different signatures that could come up. One of the things that was emphasized is that the signatures of generic early universe things go well beyond FNL local, which tends to be something that the cosmologists themselves fixate on, but it's worth maybe stepping back and thinking we should be taking a broader lens. We heard about 2 threshold values, FNL local of order 1 to probe additional states during inflation, FNL equilibrium of order 1 to probe sort of self or strong coupling of the inflaton. I want to come back and talk a little bit about that in a second, because it's not obvious to me that either of those can be a science driver for S5, but let me just put a pin in that for a second. I think it is clear that phenomenology of scale-dependent bias, higher order primordial functions, is much richer than a typical cosmologist thinks of, right? If you ask a cosmologist, how do you probe inflation? They'll say, oh, I'm going to measure FNL local, right? And I think we need to broaden our lens on that. And what that implies for the survey is not fully clear to me. I'll mention a few things as we go on. Okay. We heard that the primordial curvature 2-point function is primarily kinematic information on inflation. But of course, the measured 2-point function also gives access to late-time physics like ineffective neutrino mass and so on. And studying galaxies or the laminar forest of gas gives access to bias. And one of the things we did hear a lot about was how much information there can be in scale-dependent bias. There's a very rich phenomenology of scale-dependent bias. We heard about light particles. I loved this one, massive-ish particles, isocurvature modes, equivalence principle violation, and so on. I think my take-home message of all of that was just think beyond FNL over K squared, but you can take away your own if you want. I think understanding any of the signals we find will be fascinating and complex, but I hope we're in the situation where that's our problem, right, is to try and understand what we found rather than staring at zero. Monotonic scale-dependent bias is the thing that most people think of when people say scale-dependent bias. And my worry is that it's not obvious that that's a killer app for a future spectroscopic survey. And here's my reasoning. Even in the most optimistic scenarios, Spec S5 comes after SpherX LSST, some combination of SO and S4, which is less clear than it was maybe a day or two ago. And what we're prioritizing, what do we bring to the table? What's special about us is excellent radial resolution, a large number of modes. So just running through the scenarios, right? Suppose some combination of SpherX, LSST, and the CMB using multi-tracer or individually or however they do it, find something. Is stage 5 what you would design to confirm that measurement? It seems unlikely to me that that's what I would do. And so that, that doesn't go great. Suppose they don't find something. Is that a great science case for Spec S5? I mean, it doesn't sound like either way this is great. On the other hand, I can think of a scenario in which this might work. So suppose SpherX and LSST and CMB do their best, but it turns out that the systematics on large scales are just really hard. I don't know if that's going to be the case, but suppose that's the case. I can't use very low K. I don't know what K min will be, 10 minus 3, I don't know, pick a number. Then I'd be forced to rely on higher order information at higher K in order to get at this kind of science, right? And now this is something that Spec S5 actually has some kind of hope of doing. I can do combinations of high K power that get access to the long wavelength modes. You could imagine playing various games. What is very unclear to me, but I think we could actually compute, is whether we can achieve any interesting benchmarks in that scenario. I don't know if that's true or not, but if we could, then I think we could make this a science case for Spec S5. We can't, it feels much less clear. So a simple calculation we could do is we could try and, see how the various forecasts depend on K min and see if I can get to really interesting benchmarks if I lose all the modes below some value, right? And then somehow tie that to what we think the systematics might be. Okay, so that's one thought. Some of the scale-dependent bias produces oscillations. From the point of view of measuring the power spectrum, whether it's in the primordial power spectrum or whether it's in the bias, I kind of sort of don't care. I mean, it's a signal that I can go after. I'm going to return to these a little bit later on when I talk about features, which are also going to give me oscillatory things. So, but just put that in the back of your mind. There was a bunch of discussion about not going up the hierarchy of endpoint functions, but talking about sort of, a very, very, very high N. And so looking in particular in position space, this could in principle increase the reach for very massive particles. I don't know the right way to search for these things. I mean, presumably some sort of match filter, but I don't know what it is. In particular, I don't know what the appropriate thresholds or special model signals are. I mean, is there equivalent to sort of, I don't know, Starobinsky inflation that sets some particular feature size or something I'd like to go after? And I don't know how this drives the survey design. So, what drives the survey design, what the theoretical targets or templates are, and what we should be optimizing for are not clear to me. But this could, in principle, be quite a good science case, especially, say, for the higher density sample that we're talking about. So that's a thing that I think it would be great to drill into more. I would like to learn more about it. It's a possible signature we can go after. Higher order functions, in principle, provide a massive amount of information. Self-interactions, new particles, thermodynamical states, distributive systems, particle scattering, isocurvature modes, equivalence principle violations, et cetera, et cetera. 3D information is giving me much tighter error bars in the many tens of megaparsec scales, less so in the hundreds of megaparsecs to gigaparsec scales. We need new ideas for trying to meet these theoretical thresholds. If I really want to get to FNL equilateral of 1, that's going to be really tough. So I think the open question there in terms of that is, can I actually meet, FNL of the appropriate type equals 1, or is that out of reach? Right now, I haven't seen a compelling argument that we can get to FNL of 1 beyond local non-Gaussianity. Okay. So primordial features, one of the things that was pointed out multiple times by many speakers was that primordial dynamics can exhibit very significant departures from scale invariance. In some sense, this is generic, it's ubiquitous in non-minimal models. We heard different ways of thinking about this from various speakers, but it's the kind of thing that does show up. If there are any features in the inflationary potential, they could lead to features in P of K. Interactions with other fields can modify things and lead to features. You can have isolated features. There's a broad phenomenology of what could be done. The features can be in the 2-point function. They can be in the higher order functions. They can be correlated between the 2-point function and the higher order function. There's a very rich thing you can do here. And even upper limits can inform our model building efforts in much the same way as, current upper limits on R are already informing things about what we know about inflation. Okay. There's also not so primordial features. I had no idea what to call these. But these are things like the running of the spectral index. Well, I guess that is mostly primordial. Dark acoustic oscillations, the magical cosmological collider, self-interactions in the dark matter or neutrinos, all of those kind of things will lead to features in the power spectrum. They may not have come from inflation, but there's still features in the power spectrum. These are all targets that we can go after, right? Okay. So let me call these quasi-primordial features. This is a signal for which large-scale structure in 3 dimensions really shines. We're already beating the CMB, right, in this particular range. It's much easier to disentangle from astrophysics and nonlinear evolution than many of the other things we've talked about. And if you ask, what would you do to do really well on features? Well, it kind of drives you to a large number of modes. And so that's more or less the survey we've shown we can kind of sort of already build, right? So this is a very compelling argument for those of us who've been thinking along this direction already. One thing I didn't understand is what requirements on survey uniformity do these kind of things do? We talked a lot about statistical reach. We haven't talked too much about systematics, but we can come back to that at some other time. One of the nice things about this, if we made this a science driver, is that it pushes the design in a way that allows many other science cases. So this is a little bit like ineffective for CMBS4, right? It's the kind of thing that would push you in a direction you'd like to have the design go anyway. So if I made this a level 1 requirement, that would automatically bring in, you know, design elements that would then be useful for a whole bunch of other science cases. So that's great. The problem with this argument is that things like the amplitude, the scale dependence, and so on, they're incredibly theory dependent. It's very hard to motivate any particular threshold. I think it would be very difficult to write something saying, you know, if we get to 10 to the minus 3, that's it. We've ruled out all possible interesting models of inflation or something, right? I don't think we can do something like that. So is there some way in which I can motivate interesting models, right? So the CMBS4 people played this game really, really well. They said, you know, sure, there are models down there that have R of 10 to the minus 10, but there's these interesting models we'd love to go after that have, you know, R's right where I could see it, right? Is there something vaguely similar that we could do, right? That would be good. There's no real reason the universe has to make the dark sector simple. We could have multiple dark matter particles, dark radiation, various interactions. A whole bunch of these models do impact large-scale structure. Some of them interact with these existing tensions in interesting ways, solving or alleviating, or whatever the right word is you'd like to do. This wasn't really highlighted in the SNOMAS or P5, you know, case for Spec S5 almost at all. It was barely even mentioned, but I think it could be a lot worth developing. So that is a direction that I think we should be looking into in more detail. One thing that caught my attention, it was mentioned by a couple of different speakers during the conference, is this question of the dark matter case and fractional dark matter, and this interaction between the sort of the local universe versions of searching for dark matter and what we might get, for example, with the high redshift survey. So, you know, there's multiple ways of surfing to dark matter. One of the things that, you know, if I'm looking for decay products like photons or something, it's great because I get to access the entire rest mass energy of this thing. If I'm doing large scale structure, I have to access only you know, the momentum part of that. So rather than MC squared, I've got MV and it's cold, so B small. So that's not good. And we already have fairly tight constraints over much of the K range that LSS is sensitive to, right? So it's not like a, you know, 100% deviation at K of 0.1 is an allowed thing. On the other hand, we heard several times during this meeting that if the dark matter is not a single particle, if there's some kind of axiverse or something, and there's a spectrum of things, I could have that, you know, the light-ish part is only, I don't know, 5%, 10% of all of the matter density, in which case, what I really want to do is do a very, very precise measurement on, you know, large scales, the kind of scales that we have access to, rather than looking for an order unity signature at higher K. So that's a situation where having a well-controlled theory with minimal astrophysical assumptions is incredibly powerful because I really can drill down and find you a 1% component of the dark matter, for example. By contrast, the small scales are excellent when the expected signal is order unity, because then things like uncertainty due to astrophysics, you know, don't really matter. If there's just no power there, there's no power there, right? So that's an easy-ish argument to make. This is similar to the argument that was made, you know, for the abundance of clusters as a function of redshift to show that omega matter couldn't be 1, right? I mean, I'm looking for an exponential signal. Who cares if the error bar is 20%, right? I think what Spec S5 does in this regime of exponential suppression is a fantastic question that we heard multiple times. I think that is a topic of a different conference. I think we should organize said conference. I hereby anti-volunteer to organize that conference, but I think someone should do it. I think, you know, because we haven't really talked very much at all about the sort of the other, you know, the other cases of what Spec S5 will do. It's an amazing instrument. It would do incredibly on that kind of science, but that's not what I'm talking about. We did talk a little bit about open questions about going beyond EFT in the dark matter sector. I don't have anything interesting to add there. One exciting thing was this fifth forces discussion that came up a few times during the meeting. We're already doing much better than earlier limits. We're constraining long-range forces at the 0.1% level. We heard from Emanuele some of the reasons why this works so well. This is a situation where the CMB is disadvantaged compared to large-scale structure. So this is another area where Spec S5 could naturally just shine. This is something we do better than almost anyone else could do. And this may be the one case where we want a higher number density. I think exploring what we actually want to do, how we want to do that, drilling down to actual numbers would be really, really useful to do. We heard a bunch about simulations. You know, Spec S5 is designed to have a bunch of these different sub-surveys. There's a high redshift, large volume, and a low redshift, high number density that are quite different. The high Z part is easy, see earlier definition, for theorists, but it's particularly challenging for simulators because I require a very large volume and I require extremely high mass resolution, and I have to do both of those while working with extremely tiny statistical error bars. So this is, you know, the worst thing you could ever tell a simulator to do. And so to the extent that we can or need simulations, this is a conversation we're going to need to have. This isn't going to happen by accident. You know, someone was accidentally running a simulation and it's perfect for what we need. That's not going to happen. The high number density case, by the way, isn't exactly trivial because the statistical error bars are already below 0.1%. So, you know, this is not something, again, that's going to happen by accident, but nonetheless, perhaps a little easier than the high Z part. We heard lots of different ways to improve the simulations. I think this question of how we combine theory, AI, simulations in a Spec S5 plus other surveys world is a great topic that someone should think about. Precisely what lives inside the collaboration versus what work is inspired by the kind of science we want to go after is less clear to me. Are we going to have simulations spanning multiple surveys, or are we going to have each survey responsible for its own? That's way above my pay grade, but it's an interesting question. All right. Synergies with other probes. I mean, we are entering the multi-survey decade. This has been pointed out by many people many times. It's very promising. Thinking across surveys is hard, but working across surveys is even harder. The argument that people often make is that, you know, this can mitigate the systematics for our core science and it provides lots of opportunities to extend the science reach. This is all absolutely true. We heard during this meeting about CMB lensing, KSZ tomography, intrinsic alignments, moving lens effect, delensing B modes, lots of different things. Strong constraints on neutrino physics, scale-dependent bias. All of these things came in multiple times. There's just a few things to say about that. I think, you know, the current plan for Spec S5 is we're going to cover the northern and the southern hemispheres. So we can't do much better than that. We're going to overlap with as many surveys as we can. I think it's very obvious that Spec S5 is powerful enough to do many, many, many things in support of other surveys. That case, I think, is really easy. But, you know, no one's going to fund Spec S5 to be a support, you know, animal for some other survey. So are there joint goals that would be particularly noteworthy, right? If we have those that we can, you know, motivate, I think that would be much nicer. There will definitely be a section of some proposal that says, wouldn't it be great if you already funded us to do this? Then we'd help out these other guys, right? But that's not what we hang out on. So what are our next steps? Well, during Snowmass, the case was really made on this sort of fundamental physics, prominently featuring inflation, and in particular, primordial non-Gaussianity in features. Those were the things we presented. Those were the things that the white papers really focused on. The inflation science was pulled out by the P5 report, but in a really generic way. You saw the quote earlier. They didn't say, oh, you have to do primordial features, right? They left it kind of open what kind of goal we could go after. We have to lay out the specifics of the Spec S5 science case pretty early, and that is then going to flow down to the science requirements and design. So just as, you know, one example for DESI, you know, the science case was dark energy, and it was a decade before first light, right? That's when we kind of started this process. So if we want to do this in the mid-2030s, that means we need the science case now. We'd like to write a science book to lay out a more specific science case than what appeared in P5, which is very, very generic. We're hoping to use the information that we got from this meeting as part of that. Ideally, we'd like to come together over the next year, possibly with future meetings or conferences to be determined. If you're interested at all in contributing to any of this, if you think you have a science case that should inform the design, if you think there's something that we could tweak that would just make this whole process much, much better for you, please contact us. Beware, if you do contact us, be prepared to iterate. We're going to ask questions, right, and ask you to flesh that out. But I think this would be an opportunity for you to, to enhance Spec S5 in the directions that you think it should be going. Okay, so finally, I need to thank a few people. First off, thanks to all our hardworking staff. Without literally none of this would have been pulled off. So in particular, Tammy Blackwell and Liz Worthy, who were working the front desk with Adam, Jeff Anderson, who helped with all the web page and everything, and Jill Stark over in conference services. So maybe we can give them a round of applause. They're out there, hopefully. Thanks to our LOC, who've been running around with the microphones and generally keeping everyone on time. So Satya, Edmund, Roger, and Noah, thank you very much. The SOC, who met on very many telecons, Kyle, Simone, Vera, Dan, Marilena, and David. So thank you very much for all that work. Thanks to all the speakers and panelists. I was going to type in the names, but I didn't. But you know who you are. So thank you very much. It was great. The presentations were fantastic. So round of applause. And thanks to everybody for the questions, the great conversations over coffee, and all the rest of it. Thanks for a productive and engaging meeting. And as a famous scientist once said, carpe noctem. So thank you very much. And I think we're done, right? Questions?
Hey, we're done.
We're done. Okay, we're done.
I love how you left that. Contact us. You need to budget us.